This conference will now be recorded.
Hello, everybody. Jordan Garth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 42. Hope everybody's staying well. We got a great presentation today. Also a lot of active weather across the country. Today's presentation, utilizing the minimum flash area gridded product to understand thunderstorm lightning activity. Our presenter is Joseph Patton, Assistant Research Scientist with the Cooperative Institute for Satellite Earth System Studies at the University of Maryland, College Park. Our facilitator, Frank Alsheimer, Science and Operations Officer at the Columbia, South Carolina Weather Forecast Office. Just a few reminders before we get started today that this session is being recorded. So if your colleagues aren't able to join us, you can point them to the recording later. We will have an opportunity for Q&A after the presentation. Please post your questions in the chat room and we will field them after Joseph's presentation. We are always looking for future presenters, so if you have an application you'd like to share with the field, get in touch with us. And the training team can help create training materials that may be unavailable or point you to ones you may be unaware of. And Brian Mata, the Office of the Chief Learning Officer, can help you with that. I'd just like to thank the TELRES team, particularly Kashad Bowman, Office of the Chief Learning Officer, and the GOZAR and JPSS program. Really appreciate Kashad, Lee, and members of the TELRES team for everything they do to get us ready for these weekly seminars. Without further ado, I'd like to introduce Joseph Patton. As I mentioned, he's Assistant Research Scientist at University of Maryland, College Park, focusing on lightning research and training. His current position involves studying operational forecasting techniques using the Geostationary Lightning Mapper and creating training materials based on lightning information from the GLM for forecasters around the Western Hemisphere. Joseph graduated from the University of Oklahoma in 2015 with a Bachelor in Meteorology and Florida State University in 2017 with a Master's. He was an operational meteorologist at the NWS office in Goodland, Kansas, before joining CISESS in the DC metro area. Joseph, welcome to the Satellite Book Club.
Thank you so much for that introduction. And good afternoon or good morning, depending on where you are in the audience are today. Thank you for having me. So today we're going to be talking about the minimum flash area gridded product. And I wanted to start off with this image here that shows a flash from the perspective of GOES 16 and GOES 17 GLMs. And this multi-second flash, not only because it's an interesting video, but also to illustrate the need for the gridded GLM products. You know, while this level of detail is fascinating to watch unfold, especially at this scale, products like this are unlikely to find a good home on a busy operations floor. So the gridded GLM products are help quantify and summarize these detailed lightning observations, and that results in operational products which fit better within an operational environment. So my talk today is going to be focusing on one of those three GLM gridded products available to forecasters, and that's minimum flash area. So starting off with a quick review of what the GLM or the Geostationary Lightning Mapper is. It's an instrument that's aboard both GOES East and GOES West that are together able to observe lightning across pretty much most of the Western Hemisphere, especially where lightning is occurring towards the middle latitudes and the equator. The figure to the right shows the nominal field of view of both of these instruments combined. And each GLM grid cell is about 8 kilometers by 8 kilometers. So flashes observed by the GLM are then processed into 3 gridded products, and those 3 gridded products are available to NWS forecasters, and they're gridded to quickly convey lightning activity or lightning information to forecasters. So the 3 gridded products are 1, flash extent density, or FED, and that's essentially just a count per unit time of how many flashes are occurring within each grid cell during a given time period, usually either 1 minute or 5 minutes. So how many flashes are coincident with each grid cell? That's FED. And the second one is total optical energy, or TOE, And that's an accumulation of all the optical energy observed within each grid cell during that specified time period. So think of it as just how much brightness, literally how much energy is being received by the instrument within each 8 kilometer by 8 kilometer grid cell. And then finally, the third gridded product, which we're going to explore more today, is minimum flash area, or MFA. And that's the area, that represents the area of the smallest flash that is occurring within each GLM grid cell during that time period. So of all the flashes that do occur, what's the area of the smallest flash on that pixel? That's what MFA represents. And we're gonna explore why that flash size, especially the smallest flash size, is so important. So as we said, minimum flash area is the smallest flash within each grid cell as observed by the GLM. MFA has replaced average flash area since the MFA grids more clearly accentuate the flash size differential. You know, they more clearly pick out the smallest and the largest flashes, and that makes them more operationally useful to tell you a little bit more information about what's going on with the lightning activity. And this is just an example of a QLCS from the Central United States. So frequent smaller flashes typically indicate the occurrence of intense or strengthening convection, and larger flashes sometimes are associated with weakening convection, but also can indicate well-defined storm systems, such as the trailing stratiform region of a QLCS or the anvil region of discrete convection. So the occurrence and the relative position of those large GLM flashes, that is really indicative of the path charged particles travel outside the updraft. So if you've got a system where it's trying to become more linear and starting to develop a trailing stratiform region, you can observe those very large flashes start to shift into that trailing or backside of the convective system. And then finally, the robustness and displacement of that lightning within the anvil and stratiform regions is descriptive of that storm system evolution and severe weather potential. So if you can observe the convective mode changing as the larger flashes, according to minimum flash area, start to shift from more of an anvil region, maybe out ahead of the storm with discrete convection, to a more trailing stratiform region, back behind the storm as the convective mode shifts to linear, then that could be an indication that you've got a changing severe weather potential. Maybe I'm not as worried about hail or tornadoes. Now I can start to focus my attention on a growing wind threat, because this lightning activity, the gridded minimum flash area product, has told me the lightning activity is changing within this convective system. So there are essentially 3 primary minimum flash area applications. And the first is to detect and monitor that initial thunderstorm growth. So the MFA color map, it really hits home, it accentuates those smallest flashes, which are those gold or yellow grid cells, which are shown in the example on the right. And those, you will often see those in the initial convection or convective initiation to highlight, and that can highlight the earliest lightning within storms. So that gives you a clue. Okay, we now have our storms developing lightning, and then in addition, the MFA provides a visual cue to help quantify subsequent storm growth. So as those storms continue to grow, then you will notice the MFA highlight that storm growth, because the lower MFA values tend to indicate strengthening convection. And that leads well into the next point. So monitoring convective mode and storm evolution. So that MFA is indicative of a storm life cycle. So if you've got frequent smaller flashes, typically less than 300 square kilometers, then that's going to be most likely found within the strengthening storm cores of the most intense convection. And then as the minimum flash area shifts to more larger flashes, so greater than 600 square kilometers, that would be an example or a situation where the storm, that section of a storm or the storm in general may be weakening. So that's highlighted by the example on the right, where the red ovals highlight strengthening storm cores with your smaller MFA pixels, and then the larger MFA pixels on the southern side of that system could indicate weakening for that convective system. And noticing the consistency between scans is a thing too. So if you see consistently low MFA values, that gives you a more robust idea that that part of a storm may be strengthening, or that storm, if it's discrete, may be strengthening. And then finally, you can monitor the lightning aerial extent. So extensive anvil and stratiform flashes often result in very large MFA values because since they're the only lightning strike happening in that area and they're very large, those large MFA values, which show up often as purple pixels, purple grid cells will pop out. So the regions with very large MFA are also important due to their less obvious risk of lightning, especially well behind the leading edge of something like a QLCS. And those often represent cloud-to-ground lightning strikes, which can be an important consideration for IDSS operations. So just quickly starting off with an example of why the MFA gridded product in and of itself is an important addition to all the other lightning products. We see here, this is an example from off the coast of Florida in the Atlantic Ocean. And if you just look at FED, just look at flash intensity and total optical energy, you don't see a lot of texture when it comes to determining which of these storms may be strengthening or which of these storms may be weakening. But once you analyze that in the perspective of adding in MFA or minimum flash area, you can see all this rich texture show up that says, oh, this storm may be strengthening, this storm's probably weakening, and that can direct your attention towards the storms if you were, say, in a warning environment, which may need to be watched or monitored more closely. So there's little contrast in the FED, but the MFA provides this new context on the variability of flash size, and that in and of itself can be a valuable addition to any warning operation or operational environment. So the hazardous weather testbed ran several use cases trying to gauge how forecasters assessed or liked the utility of minimum flash area, and most of the cases showed that the MFA gridded product was very important to understanding lightning activity and providing that context on how storms are evolving in time. So one forecaster said from an IDSS standpoint, MFA and FED proved it's necessary to look at both the GLM gridded products and ground-based lightning networks to see the total lightning picture. So really you have to use them all in concert with each other. And those forecasters from the hazardous weather testbed experiments ranked minimum flash area second to only FED in terms of how valuable the different lightning products were from a whole suite of lightning products to use. So here's an example of that QLCS, kind of the same one we saw earlier. We've got TOE, FED, MFA, and then we've also got radar and ground-based networks in the bottom right. And the thing that sticks out from this is kind of what we pointed out earlier. We've got strengthening storm cores highlighted by the yellow or gold MFA grid cells. And that looks like it's associated with a Boeing segment on radar. It's associated with fairly high TOE values, as well as noticeably higher FED. So we've got more frequent and smaller flashes occurring. So that's a good sanity check on what the lightning activity is telling us about how this storm system is evolving. And indeed, right after this imagery was taken, 70 to 80 mile per hour wind gusts were observed near Rockford, indicating that Boeing segment bringing stronger winds. So before we move on, something else to notice here in the context of having the radar data overlaid is that you see that you're getting the gridded products from the GLM are updating every minute, similar to how the ground-based lightning networks are updating, whereas the radar, the fastest VCP from the radar is updating only just under every 5 minutes. So that's another added advantage here, or similar to other satellite products, but these GLM gridded products are over the full disk. And so that's an extra benefit in a warning environment, is getting 4 or 5 images from MFA or FED and TOE before you get your next radar scan or complete radar VCP. So from that same QLCS, there's actually one of the other examples that we talked about earlier. So we noticed, yeah, in the white ovals, we do have our smaller MFA values. That's where we've got our higher FEDs. We've got more frequent, smaller flashes occurring. And that's in our strengthening or mature convection, either isolated or embedded, and that can suggest a growing severe weather potential. But something else to notice from this convective system is that we also have very large flashes, which are represented in this case by the purple MFA grid cells, and that's occurring in the stratiform region of this mature QLCS. So these large flashes are particularly dangerous because they can connect seemingly distant storm cores, and along their entire path, they would pose a distinct cloud to ground or CG lightning threat, which could be dangerous to life and property. So these extensive stratiform flashes, and this example is shown on the red oval, they often break the 30-30 old school lightning safety rule. So you can't, that sort of along the lines of waiting 30 minutes after the last lightning flash, and they're well behind the convective line. So someone might say, oh, it's just a little rain, no big deal. And then you get these strong CG flashes occurring in the stratiform region. So the MFA can highlight the fact that those CG flashes are occurring and can be an issue with that system going forward. So in that context, it's important to be able to understand how and when these stratiform CG flashes are occurring from an aviation and IDSS standpoint. So this is another example of the usefulness of minimum flash area. So this is an example of just more discrete convection or supercell. And before we get into the details, I want to just make a note that you may notice that there's a bit of an offset between the ground-based lightning networks, which are plotted here, and the GLM gridded products. And that's because there is the GLM data is not parallax corrected. So this is done on purpose because the GLM data it's a satellite product. So it's going to line up exactly with all the other satellite products available to you in your suite of variables to choose from or to look at. But if you try to compare it to ground-based networks, there's going to be a little bit of an offset because of how the satellite is viewing the pixels away from its center point or away from its nadir. So just to be aware that that little bit of an offset might exist. But now diving into our actual example here, the gold MFA values highlight our strong updrafts within our discrete convection or discrete supercells. And in addition, we also see that in the anvil region of these storms, we have larger flashes represented by the purple pixels. We can see kind of purple pixels surrounding our more convective or stronger convective updrafts where the smaller MFA values are. And then something else to note here is that as these the NWS warnings are overlaid from the top right panel, and especially for the trader warnings, as these warnings are issued, we can see quote unquote jumps in the flash counts for FED, and then also we see the same consistent lowering of the flash areas in MFA. And those jumps in lightning activity can often be preceded by very small MFA values. So the MFA can give you an indication that you may, as the flash sizes get smaller, we may see an increase in lightning activity. And that in and of itself may be an indicator of imminent or ongoing severe weather. So in this case, both of the tornado warnings in this example from the Texas Panhandle ended up verifying. One was an EF1 and then one was an EF2 tornado. And so the MFA can tell you, oh, I've got these strong convective updrafts. We see this jump in lightning activity, and the warnings themselves ended up verifying for this case. So in summary, the minimum flash area, it complements the FED and the TOE, the flash extent density, and the total optical energy from the GLM gridded product suite. You should be using them in concert together to help provide the most complete picture of lightning activity and its relation to the convective mode and how storms are evolving. So you can analyze where the displacement of those larger flashes are happening, whether it's in the anvil or stratiform region. Notice how those large flashes are changing with respect to the convective updrafts, and that gives you a clue as to how convective mode is changing over time, and what the severe weather potential could be, whether that's tornado, hail, or wind. And then these trends within your individual convective cells, whether they're isolated or embedded, sometimes that can be a precursor for severe weather. And that's really one of the biggest added benefits for a minimum flash area. So that's all I have to present on today. If you would like to learn more about the GLM gridded products, the NOAA VLab page is linked here, and that's an excellent resource for both literature and other examples. And I'll be happy to take any questions or comments at this time.
Thank you very much, Joseph. That was a great presentation on a piece of information that we've gotten in AWIPS fairly recently, but clearly has some uses. I want to encourage everybody to stay on for the questions and answers in our discussion afterwards. I'd also like to tell everybody that in the chat room box, you'll see a link to a feedback. If you wouldn't mind giving us a little feedback, it would be greatly appreciated. We're also going to remind you of next week's presentation. It's on Thursday, April 1st at 12 p.m. Eastern. Chad Gravel, who's the acting chief of the Science and Training Branch and Techniques Development Meteorologist from the Technology Infusion Branch, holy cow, at NWS Southern Region Headquarters, will discuss the limitations of the GOES-R series of satellites for monitoring wildfires and their methods for the mitigation. Also, if you have any questions, please feel free to contact the Tower S team, Lee Byerly and Kashad Bowman there. You got their addresses on the screen. For questions about anything to do about the SBC here or your configuration of satellite products, more information will be followed in an email from the Tower S team. So I'm going to move on to questions. Again, if you have any questions, please feel free to post them in the chat window. But as facilitator, I'm going to take facilitator's honor and ask the first couple of questions here. So the first one I would ask you is, what would you say is the most useful aspect of adding the minimum flash area product into the growing suite of products that forecasters have to use to monitor thunderstorms during warning operations?
Well, you know, that's a tough question. There's so many useful applications in my mind. I think probably the number one would be that monitoring of the convective mode. So if you notice that you've got very small flashes along a leading edge of convection, and you've got your very large flashes shifting to the stratiform region, then you know it's more of a wind threat, and that can guide your interpretation of the severe weather potential. Whereas if you've got more discrete convection, you're going to have more of those larger flashes offset maybe ahead of the storm in the anvil region. And in addition, if you've got sort of like embedded convection, maybe it's a messy day and you're trying to gauge the strength of an updraft, if you see those consistently low MFA values, that can tell you, oh, this could be a storm I should be paying attention to. because we have a localized strong updraft in this area. But if you just see like one of those gold pixels fleck up for a second, and then the minimum flash areas return to being larger values, then you know that, okay, maybe this one is not as important as other embedded updrafts within this convective system. So it's really about monitoring where your strongest updrafts are and monitoring the evolution of the convective mode.
Okay, great. I got another question for you here. Have you noticed any difference in character of the MFA product between a situation where you have strongly forced sheared convection versus weakly forced pulse type convection?
That's a great question. I personally, I've been looking at the minimum flash area gridded products in detail for several months now, and I don't know that I don't know that there is a distinct difference between those regimes. I can tell you that, if you're expecting stronger updrafts leading to more frequent lightning flashes, which are also smaller in area, that's where the MFA product is going to be useful. So in the examples I showed, some of them were from November in the central US, some of them were from out over the oceans in December, and then some of them were from last week in the Texas Panhandle. And so I think the minimum flash area is going to provide that context no matter what the convective situation is. And then it's up to the forecaster to determine, along with the other gridded products and ground-based lightning networks and what you know about meteorology, to determine what the nature of that convection is based on the information you're getting.
Okay, thanks, Joseph. Got a few comments that we've had through the chat here. One from Gary McWilliams. It's also important to note that if the radar is on the low-level fast scan, in other words, the radar has scan initiated with additional low-level values of reflectivity, the GLMs can still help you with indicating vertical development and intensification. Another comment from Bob Kulagowski, good call on the parallax. We have found that the matches between GLM and precip are improved when they are adjusted for parallax. Comment from Steve Zubrook, there's a nice 2-page quick guide on the MFA product on the VLab site. So for those of you out there who are interested in learning more, or obviously Joseph presented a lot of information here, it's not always to grab it all in one shot. Those quick guides are very helpful. Some of the specific questions, Bob Kulagowski asked, when exactly did the minimum flash area replace the area average flash area?
So it depends on when exactly the offices were installing the new update for AWIPS, but essentially all of the offices in the NWS were transitioned over to minimum flash area at some point last year or during the last year. And then that's also a good time to bring up the point that all the NWS offices should now have, as opposed to CONUS or PAC-US grids, you should just have the full disk grids from the GOES 17 and GOES 16 lightning mappers, including a minimum flash area. So a lot of your procedures may be based on those CONUS or PAC-US grids, so it's a good time as we're getting into severe season, including today, to make sure that any procedures which use the GLM gridded products are pointing towards the full disk as opposed to the now defunct CONUS grids.
Okay, thanks for that. Yeah, I knew it was relatively new myself. Couple other questions here. This from John Goff, is the color legend on the MFA product, meaning the hot colors for the smaller flashes and the cool colors for the larger flashes, that developed from prior studies or correlations to severe weather?
I'm not familiar with the development of the color scale. I will tell you that those yellow pixels correspond to 64 square kilometers, which is by definition the smallest minimum flash area because it's an 8 kilometer by 8 kilometer grid cell for the GLM gridded products. And I do believe there was research into how the color scale would be most appropriate. You know, the hazardous weather test bed did run these experiments with these gridded products and got forecaster feedback. And so I believe this standard, based on all the imagery that I've seen and been experiencing, I believe this standard color scale is pretty good. You saw the purple colors pop out for those very large flashes, and you see the gold colors pop out for those very small flashes. So I think this color scale is pretty good. And if I don't have the evidence to back it up, but I believe it's been well researched. Yes.
Okay, and a note to everybody listening, if they didn't see it going by in the chat, a link to the quick guide that was mentioned is in the chat box. You can go find that. Another question from Steve Zubrick. Do we know if the GLM MFA data are being incorporated into Prob Severe version 2 at all?
I don't know. I would not be the person to ask on that question. I'm sort of in my little GLM cave. So I don't know. Maybe someone else can answer that question for him.
Yeah, if somebody knows the answer, they can pop it into the chat box. Otherwise, we'll find a way to get back at that information. Here's one. Yeah, it looks like from Scott Radulski, not yet. Okay, let's see. The comment from Jason Jordan, who is obviously multitasking here and looking at real live data, saying that for those who are looking at data right now, the storm north of Birmingham exhibited a jump in the flash extent density and also an increase in the minimum flash area for the smallest flashes. Then it ramped down. So I'm reminding everybody that it's a good example of how to look at all the different lightning products at one time and try not to focus on any one particular product as a magic bullet for what you're doing.
Yeah, that's a really good point. You know, that's why I wanted to highlight that comment from that forecaster during the hazardous weather testbed experiment, that it's important. It proves its utility, but only in a way in which you understand the context with the other gridded products and whatever ground-based lightning networks you have available to you.
Okay, it looks like we have a question that was answered by somebody in the audience there. The question was, are there places to view the MFA online? And the answer is that it's not as of yet. There is a place, and if you're online there and want to look at the link in the chat, you can click on that link to see what images are generated. And a comment also from Steve Zubrick, what he can see is that it looks like the GLM and TOE are used, but not the MFA for Prob Severe at this time. So I think I think we've managed to answer everything that I can tell. Is there anything else out there? Let's see, looks like we got a comment from Mike Stavish in there. The research continues to unveil great ways to use this data for operational utility. Forecasters shouldn't be expected to rely on their eyeballs and subjectivity. In the heat of the moment, the products can all trend to look similar. We really need post-processing of the data into time series per cell and some of the other plots, and also maybe inclusion into Prob Severe. So I think that's everything I've got. I will appreciate everybody's participation in this terrific presentation and discussion. So I'm going to kick it back to Jordan to close us out.
Okay, thank you, Frank, and thank you, Joseph, for that great presentation. Very well received. And thank you to our audience for the questions. As a reminder, hope you'll join us next week, Thursday, April 1st. No fooling, we got Chad Gravel, and he's going to talk to us more about monitoring wildfires. Until then, feel free to get in touch with the Tower S team. I hope you continue to stay well and talk to you soon. Thank you, Frank, and thank you, Joseph.